So if we take a control volume or an open system, it can be treated as a flow system. So if we take a control volume, as we see in figure here, so where we have mass that enters the system and we have mass that leaves the system, and this mass flow rate or rate of flow of working fluid is a constant with respect to time. So mass of fluid enters and leaves the system after doing work. So we can consider any open system or a control volume. So in this case, the control volume can be the dotted line that represents the process area here. So we represent the mass flow with an M with a dot on the head of the M. This represents the mass flow rate. And here the energy is represented as in the form of enthalpy, that is H. So before understanding the different forms of energy involved in steady flow process, let's try to understand the different forms of energy. So generally when we talk about energy, so we have two types of energy. One is stored energy, the other one is energy that is in transit. So stored energy is the energy that is contained within the system boundaries. For example, we have potential energy and kinetic energy of a system. So if you see the rock which is on the cliff, so initially it is at a higher height from the reference level or the ground level. So we can say reference or datum. So from here it is at a height. So it is going to have a very high potential energy. Let's assume that it has 10 units. And it doesn't have kinetic energy as it is not moving. So once the rock falls down, somewhere in the middle of the transit, so potential energy decreases as the height is decreasing, and the kinetic energy increases because the rock is in motion. So we can say potential energy is possessed by a system because of its height. So we can write potential energy with an abbreviation PE, and it is going to be mass times acceleration due to gravity times height of the object, and the unit is joule. So if we write the expression for kinetic energy, so kinetic energy is equal to mass times velocity square divided by 2, and this 2 has a unit of joule. So if we talk about energy in transit, this type of energy crosses a system boundary. So since we are studying thermodynamics, the common example is heat and work. We can also have energies like electrical energy that crosses a system boundary. So in this case, we have a piston and a cylinder, and the red dot represents the gas system that is present inside the piston and the cylinder. And everything that is surrounding the piston and the cylinder can be called as the surroundings. So when we supply heat to the gas, so naturally the molecules get excited, their energy level increases, and they start moving very fast. So because of that, these molecules try to repel each other very fast as they carry more energy, and they try to move apart, and that's how they expand. So when we add heat to the system, that is the ideal gas, it expands. So let's assume the piston is moved by the expanding gas. So the typical examples for transit energy are heat and work. So now we know what is a steady flow system, and all we need to know is flow energy so that we can derive the flow energy equation for a steady flow process or a steady flow system. So let's assume a control volume as shown in the figure here, where mass enters and exits through the boundary. As you can see, the mass enters from the left side and leaves through the right side, and we have the control volume dots, which are the imaginary boundaries. So flow energy is the energy associated with the flow of mass across boundaries of a system. So to understand the flow energy better, so if we take two sections, that is section A and B of the gas that is moving or flowing through a steady flow system, So we can take A and B. So the displacing mass must do the work on the mass being displaced. The section A should be displaced by section B so that section B can come to the position of section A. So we can see here, so B displaces A and it is displaced through a distance. So flow energy can be given as, so we can abbreviate flow energy as FE, and it can be written as force times the distance moved. Since we are dealing with working fluid, so fluids exert pressure, and we know that pressure is force exerted over an area. So we can write it as F by A. Area is the area of cross section. We can rewrite the flow energy FV is equal to, instead of force, we are going to write it as pressure times area, P into A into distance, which we are going to represent as X. And we can rewrite this again using volume, because we know that volume V is equal to area into height, so which is nothing but A into X. So we can write it as pressure into volume. So flow energy is equal to pressure into volume, and it has a unit of Newton meter. And this volume is not just volume. So V is the volumetric flow rate, so which has a unit of meter cube per second. For unit mass of the working fluid, we can write the flow energy is equal to pressure into volume, and we can write the unit as Newton meter per second. So the total energy of a steady flow system is sum of all energies, which is equal to kinetic energy, potential energy, flow energy, internal energy, and any other energy that is added or that changes during the process. And we represent total energy with an abbreviation TE. So before deriving the steady flow energy equation, we need to understand the assumptions that we are going to make, because we are talking about ideal fluid system or ideal gas system. The rate of mass flow through the control volume is a constant. So through the control volume, so the mass flow is a constant, and rate of heat transfer is a constant, and rate of work transfer is a constant, and the state of working fluid is constant at any point. So if we consider a particular point, okay, so if we consider 2 points where the flow is happening in this direction, so if we take 2 points, so let's say point x1 and point x2, so all the state properties at the point x1 are going to be the same, and all the properties, state properties at the point x2 are going to be the same. And we are considering only potential energy, kinetic energy, and internal energy. We don't consider chemical energy, we don't consider electrical or magnetic energies for deriving the steady flow energy equations. And once again, we know that the system is an open system, and since it is an open system, there is a flow, so we have an inlet and we have an outlet, and the mass of fluid enters the system and leaves the system after doing work. So the fluid is doing work, so work is done by the fluid, and since everything that enters leaves the system outside, if we apply the law of conservation of energy, so the total energy entering the system T in is equal to the total energy that is going out of the system. So now let's learn the notations for steady flow energy equations. So on the inlet, we have the height from the datum, which is Z1, so whose unit is in meter, and at the outlet we have Z2, which is the height of the outlet from the datum. So as you can see, we consider the exact center point of the pipe to measure the height, and Z2 also has the unit meter. And if we take the inlet, like thermodynamic properties like pressure is given by P1, then we have volume, that is specific volume V1, and we have the velocity of the fluid C1, and we have the heat supplied to the system, which is Q, and the internal energy of the system being U1. And the internal energy has the unit of joule per kilogram, that is specific internal energy. And pressure is going to be, we are going to use the unit Newton per meter square. And volume is specific volume of the working substance entering the system. So we are going to take the unit meter cube per kilogram. And C is the velocity at the inlet. So we are going to take the unit meter per second. And heat is supplied to the system. Again, we are going to take joule per kilogram. So on the outlet, we have similar properties, that is P2 for pressure, V2 for specific volume, C2 for the velocity at the outlet, and internal energy of the fluid exiting after doing the work is U2, and we have work done by the fluid, which is W, and the units are the same. So we have Newton per meter square for the pressure, then we have meter cube per kilogram for volume, that is specific volume, then we have meter per second for the velocity, and for the internal energy it is specific, that is joule per kilogram, and the work is also work done per unit mass or work done per kilogram of working fluid, that is going to be joule per kilogram. So it is a steady flow system, so steady flow rate is maintained. Now to start the derivation, so we are going to take energy entering the system first. So if we take the total energy entering the system, so total energy in can be given by the sum of all energies, that is potential energy plus kinetic energy plus internal energy plus flow energy plus the heat supplied to the system. So if we write their expressions, we are talking about specific energies and specific volume. So we are going to write them without their mass. So we are going to write potential energy as G Z1 plus C1 square half of the C1 square, that is C1 square by 2, plus internal energy U1 plus flow energy P1 times specific volume at the inlet V1 plus Q. At the same time, when we are going to take the total energy that is leaving the system, T out, which can be given by, again, a similar expression, but instead of heat supplied, the working fluid does work and leave the system. So we're going to write it as sum of potential energy plus kinetic energy plus internal energy plus flow energy plus the work done by the fluid. Again, we are writing energies which are specific energy per kilogram. So we are going to take the mass component out. So the potential energy becomes Gz2 plus half of C2 square plus U2 plus P2V2 plus the work. So by applying the law of conservation of energy, we can say the total energy entering the system is equal to the total energy leaving the system. So we can say T in is equal to T out. So now we know that by the law of conservation of energy, the total energy of the fluid entering the system is equal to the total energy of the fluid leaving the system. So we can write it as, we can equate them both and we can have GC1 plus C1 square by 2 plus U1 plus P1 V1 plus Q is equal to GZ2 plus C2 square divided by 2 plus U2 plus P2 V2 plus work done. So the above equation is known as the steady flow energy equation. And when we multiply the equation by mass flow rate of the working substance throughout, then the equation represents energy flow per time. So then the equation becomes m dot gz1 plus c1 square by 2 plus, so instead of writing internal energy plus pressure volume product, we can write it as enthalpy, because enthalpy H is equal to internal energy plus pressure volume product. So we can write it as enthalpy at the inlet H1 plus Q equal to m dot gz2 plus C2 square by 2 plus enthalpy at the outlet H2 plus work done. So this represents energy flow per unit time, and the unit of energy flow per unit time is joule per second. So in addition to that, if we take the value of Q and W in the units kilojoule per kilogram, and if the enthalpies H1 and H2 are substituted in kilojoule, then the expression becomes mass flow rate Gz1 divided by 1000 plus C1 square divided by 2000 plus H1 plus Q equal to same mass flow rate, because mass flow rate is a constant, Gz2 divided by 1000 plus C2 square divided by 2000 plus enthalpy at the outlet plus work done.